Welcome back. In the last class we proved that a Galois extension of degree 6 is always solvable. Okay. Along the way we proved this important theorem which says that if you have a cyclic extension and you adjoin an alpha to both fields in the extension, you also get a cyclic extension. Okay. And the degree of the new extension divides the degree of the old extension. So the goal today is to prove the following theorem. Okay, so let me write down the theorem and we'll spend the whole class proving this. Let F be a subfield of C. Let alpha in capital alpha be a complex number, be algebraic over F. Okay, so then the following are equivalent. The three statements that I'll make are all equivalent to each other. Alpha is solvable over F, which is to say, that is, there exists a tower. I'm going to write the tower as follows. So F equals F0, F1, Fr, such that Fi over Fi minus, so let me write like this, is simple radical for all I and alpha is in Fr, right? So it is simply saying that alpha is solvable over F means alpha is in a radical extension of F, but that radical extension must be the end of a tower of simple radical extension. So this is just the definition. The second statement is there exists a tower. So in all three statements there are towers with differing properties. There exists a tower of fields. So let's call this F equals L0, L1 contained in Ln, such that of course alpha is in the end of them and each of the extensions is abelian, that is Galois plus Galois group is abelian. As we know very well, an adjective which is used for groups, if you use it for field extensions, that means that field extension is Galois and the Galois group has that adjective. So in this case it's Galois and the Galois group is abelian. In the third statement is exactly as to, except that the word abelian is replaced by cyclic. There exists a tower of fields, let's say F, again starting with F, now K0, K1 all the way up to Km, let's say, such that of course alpha is in the last one and each Ki over Ki minus 1 is cyclic, which is to say Galois plus Galois group is cyclic. Okay, so that is the three statements. Okay, so just stare at this. It's important that you understand the first statement has to do with solvability by radicals as understood before Galois, as understood for hundreds of years before Galois. 2 and 3 have to do with Galois theory, which is Galois' ingenious idea to connect field theory with group theory. So 2 and 3 are really group theoretic statements, saying that there are towers of extensions there with extensions being either abelian or cyclic. So it is important that we prove this equivalence and then we will attack the possibility of solving quintics by radicals via 2 and 3. Okay, so we have to settle once and for all the equivalence of these three statements. Okay, so I will now prove the equivalence of this. Some of this is essentially coming from the previous class where we proved that cyclic extensions are solvable. So let's see. So we are assuming that this is the new thing really. 1 to 2 is new. 2 2 to 3 is trivial, 3 to 1 is essentially done by us. So let's do 1 to 2 first, because this is the new thing. So we are assuming that alpha is solvable. So let f contained in f1, contained in f2, contained in fr. Okay, so alpha is in fr, and suppose each fi, because each fi over fi minus 1 is a simple radical extension, suppose fi is generated over fi minus 1 with by alpha I with alpha I power ni in fi minus 1. This is the meaning of the extension being simple radical. I am just giving names to the generators and the exponents, because we have now R extensions, right? So we have to keep track of all the things. So we say that f1 is generated over f0 by alpha 1, and alpha 1 power n1 is in f1 or f0, and so on. So this is the notation. Now I am going to consider the following roots of unity. So remember we have n1 through nr and alpha 1 through alpha r coming from this tower. So we take the corresponding nth roots of unity. So primitive n1th, n2th, nrth roots of unity. We can take them in C, right? Because we are working with subfields of C now. So we have completely switched over to characteristic 0 here and subfields of C in fact. So these are primitive. If n1 is 2, I take primitive second root, which is minus 1. Of course, that's already in F. But if n2 is 3, I have to take omega. If n3 is 4, I have to take I, and so on. So these are those roots of unity. Now consider following tower. So I'm going to write down the tower and I will carefully look at this. So first I'll do f0. So let me try to squeeze this here. So I do f0 adjoint zeta n1, then f0 adjoint zeta n1 and 2. Okay, so maybe I'll just go to the next page because I want to squeeze everything in the same page. So consider the following tower. Okay, so what I'll start with f0, which is of course f. Remember the given tower is this. I'm going to add all these nth roots to f0 because I want to use our original theorem about Kumar extensions. So then I'll do f zeta n1, f zeta n1 comma zeta n2, f0, and I'll one by one attach all of them, and finally attach zeta nr. And now I'll put f1 zeta. Remember f0 is contained in f1, so I'll just add all of them to f1 also. And keep doing this, and finally I'll do fr zeta n1 zeta nr. So I've changed the original fields completely. So originally we have this. So basically we add zeta n1 through zeta nr to all fi, right? So for the first one, I just break that addition into one by one. Okay. Now we want to claim that this is an extension where this is a tower where each extension is abelian, thereby proving 2. right? So of course alpha is in here. So alpha is in FR. So alpha is in FR adjoint this. You are only enlarging the field. So alpha will remain here. And 2 says there is a tower of abelian extensions with alpha being in the last one. And here is the tower with alpha in the last one. So why is this? Why is each of them abelian? So one by one let's check. What about F0 contained in F0 eta 1? This is a cyclotomic extension. So abelian. Right, so this is covered in our class about cyclotomic extensions. In general, every time you have a cyclotomic extension, recall from. So if you have cyclotomic extension, it is the Galois group is isomorphic to a subgroup of Z mod nz star. This is abelian. So this is abelian. Right. So this is just a, this is exactly the result we proved in the corresponding, the theorem in cyclotomic extensions class. Okay. So this is abelian. So let me write that here. This is abelian. What about this? This is also abelian, of course, because this is also a cyclotomic extension. You are adding zeta n2 to F zeta n1. So this is abelian. This is abelian. So all of these are abelian. So up to this, everything is abelian. So similarly, F circle zeta ni over F circle zeta n1 zeta ni minus 1 are all abelian. So from I equal to 1 to R, if you will. Okay. So these are all abelian. What about the next one? So this, let's focus on this. What about this? I claim this is also abelian. Now here is where we will use Kummer theory. Okay, so what about this? By the first observation, what we have is F1 over F0. This is cyclic, sorry, this is radical. Okay, so I now claim okay, this is also radical. So why is that? So think about this. Why is that radical? That is radical because F1 is F0 alpha 1. So F1 of zeta n1 zeta nr is F0 of zeta n1 zeta nr adjoint alpha 1. Okay. So the same thing will generate this field over this field, and alpha 1 power n1 is in F0. This implies, of course, it is in F0 power zeta n1 through zeta nr. Okay, so this is also a radical extension, right? So that is okay. But now we have a radical extension. So this is a radical extension. And what is the degree of that extension? Okay, so this radical extension contains, the base of this radical extension contains a primitive, contains zeta n1, which is a primitive nth root of unity. Sorry, n1th root of unity. So now here is some general facts. Okay, so I claim that, so what we have now shown is, so let me go back to the Kummer extension theorem that we proved. So let me explain how we use that. Okay, so I think I went way back. No, 42 or something. Okay. Yeah, so this is the Kummer extension theorem. So let's look at the main theorem. And in fact, I wanted to look at the theorem too. So if you have a field containing a primitive nth root of unity and n is the extension of that, then k is the splitting field of that. But okay, actually I do want theorem 1. So you have a field containing a primitive nth root of unity and k is the splitting field of x power n minus a, then it is cyclic. Okay, so what I want is this. Okay, so I want this statement. So if I claim that in our situation the hypothesis is satisfied, f is a field containing a primitive nth root of unity, k is the splitting field of x power n minus a, then that extension is cyclic. Okay, so primitive n1th root of unity, and this is the splitting field of x power n1 minus, so let me just rewrite this. So f1 adjoint zeta n1 to zeta nr is the splitting field right. This is clear because f1 is the splitting field of, f1 is a radical extension, it is not necessarily splitting field. So f1 over f0 is not necessarily a splitting field extension, not a normal extension. However, it is obtained by adjoining a root n1th root of alpha 1. But now in this new extension you have adjoined n1th root of alpha 1 power n1, and hence you have attached, because zeta n1 is there, in the base field, once you attach, so basically what I am saying is that let a be alpha 1 power n1, then all the n1th roots of a are in f1 power zeta n1 zeta nr. So it is a splitting field and the base field contains f0 zeta n1, hence by theorem 1 in Kummer extensions class, f1 zeta n1 zeta nr over f0 zeta n1 zeta nr is cyclic and hence abelian. Okay, so basically my goal has always been to use that theorem 1, but in order to use that I need my base field to have roots of unity, which I have achieved by adding them a priori. Okay, so I hope this is clear. So the crucial thing is theorem 1 in Kummer theory. So in order to apply theorem 1 we need the base field to contain primitive nth roots of unity, which I achieved by adding this. So this is abelian. So this is abelian. What about this? Exactly the same reason, right? This is also abelian, except that we work with n2 now, because this is an extension a priori where an n2th root is attached. So you perform the same logic, f2 or f1, but f2 adjoined all the roots, f1 adjoined all the roots. The relevant thing is only zeta n2 that is there. So by theorem 1 of Kummer extension, that is cyclic and hence abelian. So everything is abelian, right? So this tower is a tower where each extension is abelian, and hence 2 is proved. Okay, I hope this argument is clear. What we do is take the original tower where every extension is simple radical, but figure out which roots of unity are required, which come from the powers, the radicals which are attached in these simple radical extensions. Attach the roots of unity for those ni's, and then argue the initial cyclotomic extensions are all abelian by our cyclotomic extension theorem. And after that, after f0, after you attach all of them, you use Kummer theory to argue that they are all abelian. So that proves 2. Now 2 implies 1 is trivial, because remember what is 2? 2 is that there is a tower where the end field contains alpha and each is abelian. Okay, so 2 is not trivial, 2 to 1 is not trivial. So so we have to prove something. So we will show that given an abelian extension K over F, there exists a tower such that each Fi over Fi minus 1 is cyclic. Okay, so this is more or less trivial, because what do we do? So claim is this, prove. So let G be the Galois group of the original abelian extension. So this G is abelian. K over F is abelian, so it's Galois with Galois group abelian. So let H be a proper subgroup of G, proper cyclic subgroup of G. Of course, G is cyclic, then we are done. If G is cyclic, we are done, because K over F is a cyclic extension. So then we consider K power H and F. Remember, this is cyclic. Okay, so actually what I mean is, I don't need proper cyclic subgroup of G, proper cyclic, yeah, correct. So proper cyclic subgroup. So this G, this is Galois extension, I mean everything is abelian, so this is Galois extension with Galois group G mod H, and this is strictly more than 1 because it's a proper subgroup. Okay, so by induction, so apply induction to this. Okay, so note that KH, so K over KH is cyclic, this is okay, and KH over K or KH over F is Galois with abelian Galois group, right? Because G is abelian is important here. So every subgroup is normal, so every intermediate field over the base field is Galois. So the main theorem is required here. So this is abelian with the degree strictly less than the original extension. So we then induct. Okay, so this can be populated by a series of cyclic extensions, you attach one more to get the desired cyclic extension. Okay, so this proves 2 implies 1. Because if you are given a tower of abelian extensions, you expand this tower by putting in lots of subfields where each extension is cyclic. Similarly, you do that for L1 contained in L2, Ln minus 1 contained in Ln, and you get a much bigger tower, but with each of the intermediate extensions being cyclic. So 2 implies 3. Sorry, this is not 2 implies 1. I am trying to prove 2 implies 3. So given an abelian extension, it is rather easy to get a tower of cyclic extensions. So you do that for each abelian extension and you are done. Finally, 3 implies 1, and this is something that we have done essentially in a special case in the previous video, where we proved that a Galois extension of order 6 is solvable. Okay, so this is easy because the idea is that we are given. So let me just summarize the method. So F0 is K0, K1, Km or N, Km, such that alpha is in Km, each Ki over Ki minus 1 is cyclic. So what do I do here? So what we do here is, we let Ni be the extension or degree of Ki over Ki minus 1. And let us choose zeta n1 to zeta nm primitive, they are all complex numbers, primitive n1th, n2th and mth roots of unity. And then attach all of them to K0. So first we do K0, adjoint K0, zeta n1, then K0, zeta n1, zeta n2, K0, zeta n1, zeta nm, and then you do K1, zeta n1, zeta nm, all the way up to Km, zeta n1, zeta nm. Just like in the first case, 1 implies 2. Here the only difference is the ni's we have chosen are the degrees of the extensions. In 1 we have chosen the ni's to be the radicals we needed to take. Okay, so now we claim that this is the desired tower of simple radical extensions. Why is this? Of course, this is simple radical because it's a cyclotomic extension, right? Zeta n1 power n1 is 1, so that's in K1, K0. This is simple radical. This is simple radical because these are all obtained by adding an nth root of unity, a primitive nth root of unity, nth root as you vary ni. So they don't present any problem. What about this? And here is where hopefully the Galois extensions of order 6 will be recalled to your mind now. So we have K1 over K0 is cyclic. Right, that is given to be that case. So this is cyclic. Adjoin all of these. Okay, so basically I will argue just for complete clarity. So this is cyclic by the proposition, right? Remember the proposition we proved. So if you have a cyclic extension, you attach something, it will remain cyclic. And you attach one more. This is also cyclic. Because this is cyclic, you apply the proposition. And finally, K1 zeta n1 zeta nm over K0 zeta n1 zeta n m, they're all cyclic, right? So this is cyclic. So this is cyclic. First, it is cyclic. It is cyclic, but the base field contains zeta n1 and base field contains second argument is base field contains zeta n1, which is a primitive nth root of unity. And now remember, this is a extension of degree n1. So this is a divisor of n1 by the proposition that we proved. So this, whatever this n1 prime is, n1 prime divides n1. So this implies some power of zeta n1, I think it is n1 by n1 prime, is a primitive n1 prime root of unity. So I'll write this here. So this is an extension of degree n1 prime where the base field contains degree zeta n1 prime, right? Because once you have a primitive 8th root of unity, some power of it will be a primitive 4th root of unity. Okay. So once you have a primitive n1th root of unity, a suitable, and n1 prime divides n1, a suitable power of the primitive n1th root of unity will be a primitive n1 prime root of unity. So this is a cyclic extension of degree n1 prime with base field containing a primitive n1 prime root of unity. So now let's go back to one final time the lectures on cyclotomic extensions, Kummer extensions, and let's look at theorem 2. So you have a field containing a primitive nth root of unity and an extension containing a cyclic extension of that degree n, where base field contains an nth root of unity. Then K is the splitting field of some polynomial like this. That means K over F is irreducible. K over F is simple radical. So by theorem 2, Kummer extensions. So I think page 42 in this notes, K adjoined, K1 adjoined is a simple radical extension, right? Because it's obtained by adding an n1th power of n1th root of some element of this field. So similarly, so this is simple radical, this is simple radical, this is simple radical. So everything is simple radical. So alpha, which is in, of course alpha is in here, in Km, and so I'll just write it one more time. Over F0, K0, which is F, is a radical extension. So alpha is here and this is a radical extension, because this is a radical extension of this, because there is a tower starting with this, ending with this, and where each extension is a simple radical extension. This is a radical extension containing alpha, so alpha is solvable over F. So this proves the theorem that I started this class with, and now we are ready to attack the question of solving polynomials by radicals. More precisely, given a polynomial, is it solvable or not, we want to address, and in the next video we are going to settle the case of degree 1, 2, 3 and 4, and then after that we will tackle the case of degree 5. So let me stop today here, and in the next class we will continue with solving polynomials by radicals. Thank you.